That's the correctness. Basically, it's just like what I said, okay? So interval in the left subtree of node X, and let R be the set of intervals in X right subtree, okay? L is the order interval in the left subtree. If the search go right, okay, then we need to guarantee there's no interval in the L, the set of L, that will overlap with I. Okay, on the other hand, okay, if we go to the left, we need to prove that there's no interval that is stored on the right subtree, okay, that can overlap with I, okay. So it's like we need to guarantee this. Yeah. After all, we have to find one overlap interval if there's any, right? So every time we pick like one direction, we need to guarantee the other direction does not contain any possible interval that overlap the query interval. So if we go right, as I said, that means what? That means, okay, if left X, the left child is nil, so that's easy. There's nothing in the left subtree. Otherwise, if there are some nodes in the left subtree, then we know like, okay, we are comparing the left end of the interval, a query interval, left end of query interval with the n value stored in the left child, okay? So, as I said, this one, okay, must be bigger than any interval, okay, that's stored in the left subtree, okay? Or, it is we know it's the highest right endpoint among all nodes in the left subtree, right? So we know then this interval, this query interval, there's no way, I mean, this query interval can overlap with any node, any interval stored in the left subtree, okay? Because if this is n left X, then, you know, any interval stored in the left subtree, okay, it's here, here, or this one ends here, but your query interval is here, okay? So there's no overlap between the query interval and any interval in the set L. On the other hand, okay, it's if we go left, if we go left, then we know like, okay, the low I is smaller or equal to m left X, okay, which is like the high J, okay, so the highest right endpoint, okay, the right endpoint for some nodes in the left subtree, okay. So since J is in the left, in the right subtree, in left subtree, okay, this J is in the left subtree, okay, it doesn't overlap I, okay, and we know like a high I is going to be smaller than low J, okay, but because the fact that, remember, when we come here, we know there's no overlap. There's no overlap between the query interval and your X. Okay, and the fact that, okay, it is a binary search tree. Okay, it implies that for all the intervals that we store in the right subtree, okay, the low J must be smaller or equal to low I prime. So then we have this. Okay, it is impossible to have any interval in the right subtree to overlap with the query interval. Okay, so that's it for the proof. Okay, we only need to prove like one way or the other. Okay, if you go this left, there's nothing possible in the right subtree. If you go right, there's nothing possible in the left subtree. That's it. Okay, so we finished this this part, and then let me. Okay. Okay. Let me make it this clear. Okay. Skip list is not. Let me repeat. Is not part of the. It's not one chapter in your textbook. Okay. So I understand like many textbooks do not cover skip list, okay, and the fact that I will talk about skip list, okay, quickly, okay, I'm not going to cover everything, okay. If you are interested in skip list, okay, you could check out like some reference, okay, you could check out some reference. One of the references, I mean, you could find is my paper. Okay, I have a paper that was published in a IEEE transaction that use skip list. Okay, for security reason. Okay, for to be specific, it was used for authentication because we want to do quick authentication. Okay, for RFID. Large RFID, large-scale RFID system. By the way, that paper was actually my representative work, okay, when I was promoted to full professor. So it was a long time ago, yeah. But anyway, okay, so as I said, I'm only going to talk about what skip list is, okay. Why do I need to talk about this? Because, okay, remember we have two programming assignments, okay, and you have done one, okay. Tonight I'm going to upload the one homework, obviously, and the other one will be the programming assignment, okay, and the skip list, okay. Even though if you look at its name, it doesn't look like a tree, right? But it is a tree. It is not only it is a tree, it is a balanced binary search tree. Okay, so the second programming assignment involve like a programming. You write some program for the binary search tree. Okay, so yeah, so that's why I want to cover this one. Okay. So let's begin. Okay, I hope to finish this one. Okay, in about half lecture. Okay, and I will not go into much analysis. I think like analysis you could check it out by yourself. Okay. So if you want to do a search, okay, there's a, it's think about if you are given a set of numbers and you want to do search, okay, the easiest approach, because you don't know what number to search for, okay, the easiest approach is to sort the number and then put these numbers in maybe in ascending order, right? And then you search from you do binary search, right? If you don't want to spend the time for to sort this number, obviously you have to do a linear search, right? So you check out like one node at a time, okay? Put them in maybe a linked list and do start from one end and do the search, okay? So do we have like a better way to do the search? Okay, obviously binary search tree is one possible direction, right? But this idea, skip list, is a very, very special idea, okay? It's very different, okay? Because like in the previous binary search tree, or like such as binary search tree and the red-black tree, okay, that we talked about, okay? We start with a tree, right? We start with a tree. But the idea of the skip list, okay, even though I told you it's a tree, but we start from a list. Okay, this idea, okay, is a very interesting idea. It's a it's a simple, randomized dynamic search structure invented by William Poole, okay, in 1989. Okay, so actually you can see that if you know like algorithm, this subject has been there for quite a long time, right? So 1989 is quite recent. It's about like 30 years, 40, less than 40 years. Okay, so you can see that this is relatively new idea, okay, and it's easy to implement. Okay, the reason why most textbooks do not cover skip list is because, as I said, this is relatively new. Okay, a lot of textbooks cover like what we call like a traditional stuff. So this one is, well, it is not considered to be a traditional idea. Okay, and in here we maintain a dynamic set of n elements in log n time per operation in expectation and with high probability. So I probably have to talk about, do I? Okay, I will tell a little bit, because I mean, unless you understand what high probability is, like, you probably don't appreciate the idea of skip list. Okay. So anyway, let's start. Say you have a simplest data structure, sorted numbers, and you put them in the linked list. Because we are talking about lists, right? skip list, right? So it is, after all, a list. So previously I told you if the numbers are sorted, we prefer to put them in an array. Why? Because in an array, we could use index. Okay, we can utilize the index to do the binary search, right? But if it is a linked list, unfortunately, it does not have index concept. So you can only do this if you are looking for a particular number in this data structure. So this search will take linear time in worst case, right? Everybody understand that, right? So this is a very simple idea, right? So can we speed up the search? That's the interesting concept here. I mean, to be honest, like most of people, if I ask you this question, the first answer, as I said, would be, well, why don't we put these numbers in an array and the problem is solved, right? The search can take log n, right? So, great, yeah. But this guy, William Poole, it has a special idea, okay? So, for example, suppose we have two sorted linked lists. Okay, if we have two, okay, and one store all the numbers, the other one store a subset of these numbers. Okay, and each element appear in one or both lists. Okay, obviously, and we can speed up the search. How? It's going to be something like this. Remember the name. It's a skip lists. There's a plural form there. So we are talking about multiple lists. Okay, multiple lists. So here, okay, if we have something like this, okay, if you see this data structure, how do you perform the search? If I ask you, I want you to design an algorithm that can do the search more efficiently. How do you do it?这问题应该蛮简单的，你们听得懂我的问题哦？应该上课用英文已经一段时间了，希望你们，对啊，就是说，如果我们现在资料结构是这样子哦，就我们现在有一个完整的 list 在下面，上面是有一个，就是这个下面这些数字的一个子集合嘛，不完整的子集合，那它当然也是排好序的，对不对？然后它跟它下面就有重复的，它就有一个 link 连到它重复的那边 ，OK， 那这样子两个 link list， 那原来如果说你要 sorted link list， 你在下面只有一个的时候，你就是时间是 n 嘛，就是线性的。那你现在有两个的话，你会怎么做？先找上面 ，great。So you start from the top linked list. After all, you have fewer numbers, right? You have fewer numbers. 你的数字少一些嘛。譬如说，你从14，假设我们要随便讲，我们要找的数字是那个69，好不好？69，随便讲。Okay, so 14. Okay, it's not right. You skip to 34, right? Okay, the top linked list allows you to skip all the way to 34. But 34, I was talking about 69, right? 我讲69嘛，所以34也比69小。Okay, you go to the next one. It's 42. It's still smaller than 69. And the next one is what? 72. 72 is larger than 69, right? So it tells you what? It tells you that if 69 will appear here, it must appear in this range, right? So you go down here and try to do the search for 69. So, so blah, 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 blah. Unfortunately, you hit 72, and then you couldn't find 69. And then you can terminate and conclude that this number is not there, right? 你就可以下结论，就是你在这边69嘛，不在这就是你就知道69在42跟72之间，你就下来到这边去搜寻。那你搜寻到66，再下来到72，你就知道说你必须要停了，你不需要再继续搜寻，因为这是不可能，没有这个数字在这边了，对不对？所以呢，这就像什么啊？我不知道你们多少人有去日本玩过？多少人？你们有去日本玩过的话，你们有坐过他们的火车吗？台湾好像比较不流行这样子，就是日本的火车是，它有分同样一条线，它要分很多种，有所谓的 express。好吧，不，你没有去过日本没关系，你坐过高铁嘛？对，高铁总坐过。你知道高铁有时候有一些车它是有一些站不停的，你知道吗？对不对？我知道好像高铁有一班最夸张的是从高雄直接到有没有停台中我忘了，但是就高雄到台北的样子，对不对？对，那个是最 express 嘛，那其他有停比较多站的。那停最多站的，连那个一些很少人去的，像什么嘉义，它也停，对不对？但是不是很多车子会停那些，所以你可以想，下面就像是那个，就是每一站都停的，上面就像是那个有一些那种可以 express line， 就是那种快速那种列车、火车，它会跳过一些站的。那下面是 local line。那你有 links between the line at the common station， 就是这个就是因为他们都是 share 同样的站嘛。譬如说，举个例子来讲，你想要去嘉义，那你那个你从那个什么，你可以从那个台北，可能先到台中 ，OK， 他如果说坐他那个 express 先到台中，然后再换那个。一站一站都停的，对不对？就基本上类似像这样子的想法，对，所以大概是这样做，对不对？你就把它想成 subway 了，就是说像刚刚讲的火车这样子的情形。好，那 the next question. Yeah, so this is the algorithm that I was talking. We were talking about. We start from the top, right? Work right in top linked list. Until going right will go too far. And then we work down to bottom linked list, okay? And work right, to until element is found or not, okay? So that's pretty straightforward, okay? So this example is given 59. So we go this way, this way, this way. And the next one is 72. It's bigger than 59, so we go down. So 42, 50, 59, and we found it. So it's a very straightforward. So having said this, so if you are the one who designed, okay, in the previous in this example, you don't get to control which number should be promoted to the top link list, right? 你在刚刚我们讲这个例子哦，这个例子，我们现在已经给定的这个 L， 就第一个 link list， 第二个 link list 都已经给好了，对不对？但是假使你有权利去设计这架构，也就是说， 你下面当然这个 L2 不用设计啊 ，L2 就是全部的数字嘛。L2 contain all the numbers, but if you get to choose, how many, what number to put on the top linked list, and how many you should put there. 如果你有选择，去决定上面你要放几个数字，要放哪几个数字，那你要怎么办？In a subway, the popular station,如果说真的是那个 subway， 譬如说，就像我刚刚讲的说，你从高雄最快的是从高雄直接到台北，对不对？为什么从高雄到台北？因为这两个地方人最多嘛，对，有时候也要加上台中啦，高雄、台中、台北。为什么是高雄、台中、台北？因为这三个站可能人是最多的，对不对？所以就是 popular stations。Okay. But here, okay, we care about the worst case performance. Okay, 就是我们这边不是在讲那个高铁站嘛，我们不是在讲 subway， 我们没有所谓的 popular station 的概念。OK， 所以呢 ，OK， best approach 是 evenly space the nodes in L1。就是 L1 里面的数字，应该是它的间隔是一样长的，对不对？因为对称嘛，对称，对不对？因为 symmetric reason， 你应该是，就是说你如果上面会放 n 个 station， 这个 n 个 station 应该是，就是说它是一样距离的，因为 symmetric 的 reason。OK， 因为我们不知道，应该说我们假设每一个 station 的 popularity 都是一样的。应该这样讲 ，OK， 但是我们讲了这样子，也还是没有帮我们解决最后的问题。我们要放几个 station 在上面，对不对？几个 node 要放在 L1 上面。So this is an interesting one. Let's consider the search cost. The search cost is roughly L1 plus L2 divided by L1. Okay, why is it L1? L1 is top one, right? This is L1, the size of L1. Because you first do a linear search on L1 until you find that the next station goes too far, right? Okay, so the easy analysis tell you like it's a linear. It is a linear time to the number of nodes in L1, right? So that's L1, size. Plus, and then once you go down to one of the interval, okay, if you evenly space the elements in L1, okay, then each interval contains the same numbers, right? And in the worst case, you only need to go through those numbers, and you can conclude the query number is there or not, right? 你只要走过一个 interval 就好了。那一个 interval 大概是多少？是不是 the size of L2 divided by the size of L1？ 对不对？对不对？这应该蛮容易看的嘛。对，好，这个是的 cost， 这个 search 的 cost。So if you want to minimize it, okay, you want to minimize it. Okay, how do we do minimization, by the way? You 把这个东西当做一个function，你要把这个东西 minimize， 就是微分嘛，微分等于0，对不对？微分等于0，这没问题。就你就是假设你的 L2 嘛 plus L1 除以 L2， 对不对？对不对？是这样子嘛？ 你可不可以做这件事？你把 L2 就你把 L2 当做 x， 把 L1 不知道当 y， 我不要用 y 好了，因为我们这边到时候会，我怕你们会 confuse， 当做另外一个数字，随便讲，z 好了 ，z 除以 x， 对不对？这可以吧？那这会等于 f of x 嘛？对不对？因为这是根据你的 x 的多少决定的，对不对？对我们可以假设 z 是一个 constant 啊 ，z 是一个 constant， 假设，那你要让这个东西出现极值，就微分嘛，微分，所以 f prime 极值出现就是 f， 哎，又没水了。就 f prime x 等于0嘛，对不对？然后 f prime 是什么？你 x 这边变1嘛，那这是变什么？这 z 乘上 x 的负1次方，对不对？变成减掉 z 乘上 x 负2次方，这有没有问题？这有问题吗？应该还好吧，等于0。所以说呢，你把它写出来的话，是不是应该是这样子？应该是这个 L1 的平方会等于 L2 啊，对不对 ？L1 的平方等于 L2， 你自己把这移项以后，对啊，然后自己看一下，是不是应该是 z 等于 x 平方？对 ，z 等于 x 平方，那我们的 z 就是 L1 嘛 ，L1 的 size。x 就是 L2 的 size， 对不对？所以就有这个东西。那然后我们就知道说 L1 的 size 应该是 L2 的开根号 ，right？ 可以吗？这个推导应该很简单吧 ？Should be easy, right? So this is like, you know. If we want to minimize this value, so you should set the size of L1 to be roughly, the square root of n. So far, so good, right? Okay. But this is a two-linked list. Okay. So L1 size is square root of n. L2 size is n, obviously. Okay. And the search cost is going to be this one. You plug in this square root of n in this formula. You get like 2 times square root of n. Okay? So this is like, again, straightforward. But obviously you can generalize this, right? You can generalize this idea to be, multiple linked lists, right? To have multiple linked lists. Okay? If it's 2 sorted lists, then it's going to be 2 times square root of n. If it's 3, it's going to be 3 times squared, n to the power of like 1 over 3, okay? And if it's k sorted list, it's k times, n to the power of 1 over k, okay? Then the best one actually happens when you have log n number of sorted lists. And it's going to be 2 times log n. This analysis is, again, very straightforward, okay, just like what we did for 2 linked lists, okay? So I'll skip like this analysis. The important thing is to tell you, okay, the concept here, okay? So now, okay, so we are facing this log n number of linked lists, okay? So it's like the log n sorted linked lists are likely a binary tree. Why? Because if you look at here, This is like a part of the link, skip list, part of skip list, because obviously you may have more numbers on the right hand side. But if you look at this one, don't you feel like this looks very similar to a tree? It is, okay, you could, conceptually consider the skip list a binary search tree, actually, okay? I mean, it's kind of. The 14 is the root of this subtree to here. Okay? And then, for example, I probably should start from here. 14 here is the root of this one. And this one is a root of this subtree, and so on. Okay, it's just like if you look at this, then skip list a little bit like skewed. You will feel like it is a binary search tree. Okay. This is actually you can consider it's a level linked B plus tree, but because we didn't cover B plus tree, so I'll stop the discussion. Okay, but if you're interested, you can check out what B plus tree is. Okay, by yourself. Okay, so anyway, so this is skip list, and the search in this log n linked list, okay, is going to be, for example, if you are search 72, so we are doing from 14 to 79. Okay, so it's we go too far. We go down one level, 14 to 50, so we go to 50. 50, okay, next one is 79. Again, we go too far, so we go down. 50, 66, we go here. And then 66, 79, oh, we go too far, we go down. 66 and 72. So you can see that the similar idea applies here, right? Okay. So we know like ideal skip list, okay, is this log n linked list structure. Okay, this is the ideal skip list. Okay, this is skip list data structure. We maintain it roughly this structure, subject to updates. Update include insert and delete. Okay, so how do we do it? Okay, or put it another way, how do we create skip lists from the ground up? Okay, to insert element X into a skip list. Okay, so first you do a search, okay, X, okay, until you find where X fits in bottom list. So it's just like you are doing a search for X. Obviously you are going all the way down to the bottom, right? Okay, because X is not there, right? So you are going down, okay, eventually to the bottom. And you will be able to find a place that fits X, right? Fits X. So you put it in, you always insert this new element into bottom list first. And bottom list contains all elements, obviously. Okay, this is actually invariant for our skip list. Okay, so as for how, whether or not we should insert some elements of the list above the bottom list, okay, how to do that? Okay, to which other list should we add X? That's a interesting question. I mean, we could do it like this. It's like a equally spacing, right? Equally spacing. But if you do this, obviously, this arrangement or the update is going to be much more costly, right? Much more costly. So we take the what should I say, like a randomized approach. Randomized approach. Okay. So we flip a coin. Okay, as long as it's fair. Okay. If it's head, we promote X to next level, up, and flip again. Okay, because it's log n, right? So basically, like every skip every list above 1 has like about like half of the previous list in terms of the size, right? Like the bottom list, I mean, the size is n. The second to the bottom, the size is n divided by 2, and then the top, the next one is n divided by 4, and so on, right? So basically, just throw a dice. Throw a coin. Okay, throw a coin because it's like a head or tail. Okay, just 2 outcomes. Okay, so probability of this promotion to the next level is going to be, half, right? So this is like a randomized approach. So on average, okay, you have half of the chance, half of the elements will be promoted to level 0. Okay, and 1/4 of the elements will be promoted to like a level 1. The 1/8 of element will be promoted to level 2, and so on. So this is exactly what we are looking for, right? Yeah. So, and this is approximately balanced, actually. Approximately balanced. It's not because there are some like randomness associated with that, but it is roughly balanced. So you can try to build a skip list from scratch by repeated insertion using a real coin. You can give it a shot. That's what I'm going to ask you to do. Okay, you have seen like so many different binary search tree structure. I want you to do a comparisons between them, just like the first programming assignment. Okay, you are comparing different sorting algorithms, right? So this one is going to you are going to compare different binary search tree. Okay. So, but we probably want to do a little bit change here. Okay, we can add a special negative infinite value to every list. Okay, at the leftmost end. Okay. This one will not affect your algorithm, search algorithm, but this will come very handy. Okay. If we have that, it's like you can use that as like sentinel， 就是哨兵。现在讲哨兵是不是？你们哪个去看过《雷霆特工队》啊？没有看，可以看。对啊，我上个周末我去看，对啊，还不错。OK， 不过它不叫 sentinel， 它叫 Sentry 是不是？对 ，Anyway， 好。So let's now we can formally define the skip list. The skip list is the result of insertions from an initially empty structure. Okay, when we say empty, it contains just like a negative infinite. Okay, so insert X. Use random coin flip to decide the promotion level. Okay, and delete X, remove X from all lists containing it. very simple. Delete is very, very simple. Just remove it from all the lists that contain X. Okay? So this, how good are skip lists, okay, in terms of speed and in terms of balance? Intuition tells you it's pretty good on average. And so it's actually really, really good, almost always, okay? Even though we are building it by, in random, but it's actually very, very good. But I think wait a moment. It's already 10:10. Sorry. Yeah. Let's take a 10 minutes break. When we come back, I think I will skip the following analysis for skip list, because you now know what skip list is, right? Okay. So if you're interested in knowing more about its performance, I have the slides, and I think I gave you the PDF file, right? 你们有 PDF 档吗？对，你们可以看那个 you can read the following slides to learn about this, but I will not go into a detail in the class, okay? Because I think by the way, we only have how many lectures do we have? Today is 今天是5月几号？5月7号。I think we only have about 3 more lectures. 3 more lectures. 6月的第一个礼拜，我们会是期末考。6月的第二礼拜，你们会考写程式的部分。第二个礼拜应该是礼拜2 ，OK， 就是跟上次程式一样是礼拜2。那这一次我们会全部用电脑教室，就像我上次讲的 ，OK。So we only have 3 lectures left, so I prefer to cover some more important stuff. Okay, so I will end here because I have to cover it because this is about this has something to do with my second programming assignment. Okay, yeah, that's it. So let's take 10 minutes break.